So lesson B here, probability in a finite sample space, is going to draw on a lot of the stuff that we talked about in the last lesson about event spaces and sample spaces. And what we want to do today is we want to be able to determine the probability of some event that occurs inside of our sample space. And we're going to use a form, sort of a variation of this formula that we saw up here at the beginning of the last lesson, that a probability is kind of the number of ways something can occur divided by the total possible number of outcomes. Let's just take this formula right here and put it into the language of sets and event spaces and sample spaces that we used in the last lesson. So if we have some event space E, which is, I'm going to add in this little symbol here, which means it is a subset of sample space S. So some event space in our sample space S, E, and we read this as E is a subset of S. Okay. So for an event space, E is a subset of S. The probability of this event E, we denote probability by capital letter P, and then in brackets afterwards we say probability of, we list the thing that we're trying to find the probability of. So if we're talking about event E, the probability of event E is equal to, well, it's the number of ways that this event E can occur. And what does that mean in terms of sets? It means the number of elements in that event space for event E, okay, or the cardinality of that event space. Divided by the total number of possible outcomes. Well, what are the possible outcomes? It's the number of things that are in our sample space S. So the probability of event E is the number of elements in our event space E divided by the number of elements in our sample space. So in other words, to find out how likely E is, our event E, is to find out how many ways E can happen and divide by the number of possible things that can happen. Okay? And when we're doing this, we're making a bit of an assumption here. We're assuming that all of our outcomes are sort of equally likely here, which isn't a bad assumption at this point. So let's make this a little bit more concrete by doing an example here. 2 dice are rolled. Determine the probability of rolling doubles. Well, first, let's figure out how many things are there in our sample space. And in the last lesson, we said that if we're rolling 2 dice, the number of events, outcomes in our sample space was 36. Okay, we had 6 possibilities on one die, 6 possibilities on the other. Fundamental counting principle says we just multiply those 2 together and we get 36 possible outcomes. We are interested in the event E where they roll doubles. So let's let E be the event where doubles are rolled. If we wanted to, we could actually write out the event space for this event. We also did this in the last lesson. We said, okay, you could get 1 on one die, 1 on the other one. You could get 2 and 2. You could get 3 and 3. We could get 4 and 4. We could get 5 and 5. Or 6 and 6. That's not a very good name. 6 looks more like a 3. So we could list out the event space, but really listing out the event space is just in order to help us come up with the cardinality of our event space, or the number of elements in our event space here. So how many elements are there in E? There are 6. So there are 6 ways that you can roll doubles. So using this formula that we developed up above, we know that the probability of this event is just going to be NE over NS, or 6 over 36. So we just put this in lowest terms, 1/6. So the probability of getting doubles is 1 out of 6. That's a fairly straightforward example. Okay. Let's do one that's a little trickier and is going to bring in some of the counting techniques that we used in Unit 2 eventually. If our class is composed of 12 female students and 9 male students, which is true if everyone is here, it is not true today, but what is the probability that a student chosen at random will be female? Okay. We need two things. We need to know what our sample space is and what our event space is. Or more appropriately, we need to know the number of elements in each of those. So our sample space is just a student chosen at random. Okay. Our event space is that student chosen at random is going to be female. So in this example, what are the number of possibilities in our sample space? Okay, how many choices do we have if we choose a student at random? Well, we've got 12 female students and 9 male students, so 21 total students. So the number of things in our sample space is 21. That's the number of possible ways we could randomly choose a student. In our event space, well, how many possibilities do we have for choosing a female student? Well, if we have 12 female students in the class, there are 12 different ways that we could do that. So our probability of this event is just going to be 12 over 21, which again reduces down to 4/7. Now let's look at a little bit more complicated example here. What is the probability that a group of 4 students chosen randomly will all be female? So let's again think about what our sample space is and what our event space is. Our sample space is all of the possible groups of 4 students. Our event space here is all of the possible groups of 4 students that are all female. So if we want to figure out how many elements there are in our sample space, we need to think of how many possible ways, let's actually write this out, the number of ways a group of 4 students can be chosen. So how many ways can we choose 4 students from our class of 21 if we have no restrictions on it? Well, Jacob, you look like you wanted to say it. That would be a permutation. We want to use a combination here. So, and the key word to knowing we want to use a combination here is that word choose. We've got a set of things. We are choosing a certain number of elements out of it. So what combination do you think we're going to use here, Jacob? 21 choose 4. Okay, we've got 21 things we can choose from. We're going to pick 4 of them. And right now we don't care whether they're male, female, whatever. Okay. Now, our event space is the number of ways we can choose for female students. Okay. I shouldn't say, that's not our event space. Our event space is that the group of 4 has 4 females in it. The cardinality of it is the number of ways we can do that. So how many ways can we choose 4 female students from our class? And again, that word choose means that we're going to be using another combination. What's our combination going to be in this case? Well, how many female students do we have to choose from? We have 12 of them, and we want to choose 4. So 12 choose 4. So what's our probability going to be? the probability of this event is going to be 12 choose 4, the number of ways of choosing those 4 female students, divided by the number of possible events here, 21 choose 4, which works out to be 495 over 5,985, or 0.0827. And in a case like this, we usually express this as a percent. We get about 8.3%. So if we randomly chose 4 students, there's an 8.3% chance that that group of 4 students would be all female. Okay. All right. Let's try a similar example, a little bit trickier here. What is the probability that a group of 4 students chosen randomly will have at least one female? Okay. So once again, what is our sample space here? Well, our sample space is the same as it was before, choosing 4 students. So the number of outcomes in our sample space is going to be the same. It's still 21, choose 4. The number of possible ways we can choose 4 students out of our 21 student class. The event that we are interested in is the number is having at least one female here. Now, it's probably easier to think of this one as actually several different events combined together. We could have the event where there is 2 females, sorry, at least one. One female, an event where there are 2 females, an event where there are 3 females, and an event where there are 4 females. Okay? So this leads us to what is called the direct way of calculating this. Okay? So if we want the probability that there is going to be greater than or equal to 1 female, okay, we can calculate the probability of there being 1 female, and I'm going to shorten that up. I'm just going to write 1F. How's that? 1F plus the probability of having 2 females plus the probability of having 3 females plus the probability of having 4 females, or all females. Because those are the 4 possible cases where we have 1 or more females. So we can work out the probability of each one of these individually. And each of these is going to be a fraction here, okay, where let's just look first at the probability of having 1 female. Okay? We know the number of things that can possibly happen is going to be 24, choose 1. That's the number of things in our sample space. What are we going to have up here in our numerator? Well, if we're having 1 female, we have to look at 2 combinations here. We have to have 1 combination that represents choosing our females and 1 that represents choosing our males. So how many ways can we choose that 1 female that we want? Well, there are 12 females. We choose 1 of them. The rest of our committee is going to consist of 3 males. So we have 3 males that we want to add to the committee. We have 9 to choose from. So the possible ways of having 1 female is 12 choose 1 times 9 choose 3. What if we want 2 females on our committee? Well, there are 12 to choose from, so 12 choose 2. And then we need 2 more males to make up the rest of the committee. We have 9 males to choose from, so 9 choose 2. And again, this is all over 21 choose 4. That's it. This is females, males. Okay. What's up next? We want the probability of having 3 females on our committee. So 12, choose 3 to get our 3 females. 9, choose 1 to get our 1 male. All over 21, choose 4. And then finally, we want the probability of getting 4 females. We did that calculation in the last question. It was 12, choose 4 over 21, choose 4. And then from here, we want to work out all of these combinations. Okay. So I think the most straightforward way to do this calculation is you're going to have a string of things that are added together. 4 things. And these are just going to be the numerators of each of these terms. And then at the end, we're going to divide everything by 21, choose 4. So we know what 21, choose 4 is from the previous question. 5, 9, 8, 5. We need to work out all of these combinations up in the numerator. So 12, choose 1, 9, choose 3. Punch this in, we get 1008. 12, choose 2 times 9, choose 2. Punch this in, we get 2376. 12, choose 3 times 9, choose 1. We get 1980. And then finally, just 12, choose 4, 495. So add those all up, divide by 5985, and we end up with 0.9789, which is approximately equal to 97.9%. So if we choose 4 people at random from our class, there's a 97.9% chance that at least one of them is going to be female. Now there's a second way of doing this question, okay? What is called the indirect method. Okay? And we've used this indirect method before, okay, when we've been doing combinations. So if we want the probability that there's going to be 1 or more females, so let's say greater than or equal to 1 female, we want the total probability of everything minus the probability that there will be less than 1 female. Now, the total probability is always 1, okay, or 100%, which is just a way of saying that something in our sample space always has to happen. Okay? So if our total probability is already 1, we want to subtract from that 1, we want the probability that there will be less than 1 female on our committee. So really, this is the probability that there will be no females. So how can we calculate the probability of there being no females? Well, we know it's going to be a fraction. We know there's going to be a combination on the bottom, which is the number of ways that we can choose our 4-person committee. 21, choose 4. If we have no females on our committee, what is our committee made up of? It must be made up of 4 males. How can we choose these 4 males? Actually, I'm just going to write this over here. 1 minus the probability of 4 males. So how do we choose our 4 males? Well, we have 9 to choose from. We want to choose 4 of them. So our probability is going to be 1 minus 9 choose 4 over 21 choose 4, which is 1 minus, we get 126 over 5985, which works out to 9789 or 97.9%. Okay? Same thing we had previously. So the direct method and the indirect method should always give you the same answer here. Okay? Usually the indirect method is just a little bit shorter.